Oh, and I need the video. And I need to share, oh my God. And I need to share screen. Oh my, okay. I did hit record. We are now recording. Thank you. Yes, please yell at me. If you see that I didn't share screen, something when I'm talking to the screen, or if I didn't stop the share when I'm talking to the board. Come on. This thing's so touchy. If I touch it, see? No. It's like really sensitive. Are you kidding me? I don't even know what happened there. Let's just record the ceiling today. Come on, dude. Okay. Woo. All right, let me share the whole screen. Yeah, so, okay. Let's see, logistical stuff. So the homework's gonna be due Thursday night. I had decided the one homework this week will be due Thursday night. And I still need to post it, I'm sorry, I'll post it this morning after class. And then, like I said, there's no class Friday because I'll be out of town. I know you're sad, but anyways, so those are the main logistical things for this week. Yeah, so here, I'll show you. This is sort of interesting. If you have, let me actually do, it's called a user-defined potential. And let me actually put, so I don't know, I kept using this example, x squared plus xy. There we go. Is that it? Is that what it looks like? Maybe. And we were talking about the gradient, right, of a function and about the partial derivatives, the directional derivative. So here's a contour plot of that map. Here's not Mathematica, here's a contour plot. This is sort of the 3D surface, right? My X's and Y's and Z's. Does this match what's on the screen here? I guess it sort of does. Yeah, and notice what this app does, and I'll put a link to this. I like this app because what it does is it drops a bunch of marbles on here and then watches what happens to them as they as they fall down the surface. Although this is actually, this isn't exactly gravity. Gravity would be force because it'd be about acceleration. So that actually makes things kind of more complicated because you drop them down this ramp and it goes up the other side of the ramp. Whereas if you just want to see almost like how water would flow down the surface, right? Like it would drop right down the ramp and kind of pool here and then drop down, go down this. So it's sort of a saddle. This shape ends up being sort of a saddle, right? And so the water ends up doing that. The reason I'm talking about that is a lot of people talk about this kind of picture as a negative gradient. Because if you think about if you just put like marbles or water or whatever on the surface and let gravity do its work, it's going to go down the fastest. It's going to go down the fastest possible route, right? So it will go like the opposite of the gradient. Remember, the gradient goes up is the direction of the fastest increase. So if you want the direction of fastest decrease, you can actually picture that by some sort of dropping marbles on a surface or like just flowing water down a surface. I'm going to write a bunch of this down. I just wanted to sort of show you this picture, and I'll show you some of these pictures as we go in class. But let me remind you what we said about the gradient last time, at least the 2D gradient. I want to get into the 3D gradient today. Stop the share. Okay, so yeah, so we had this geometric interpretation of the 2D gradient. And just remember, like, given z equals f of x comma y, grad f is also given by this upside down triangle, is the vector whose coordinates are made up out of the partials. So for example, let's keep using this example. If that's our function, then the gradient is 2x plus y comma x. It's the example we were looking at last time. If we take the partials, and if we want the gradient at a point, which I think we did, like the point 3 comma -1, that would be just plug in and we would get a specific vector, right? So that's what the gradient is. And the geometric interpretations are that its direction is the direction of maximum increase of f at the point, at whatever point P you're looking at, right? So for a specific, for like a specific one like this. So at a point P, I guess I should say. It's the maximum increase of f at P. The magnitude is that amount of maximum increase, is that rate of increase. Yeah, maximum rate of increase. Like here, in this example, the magnitude of this vector is the square root of 34, which is like 5.8 something. Remember, that was like the largest number we got in our slopes. It was like 5.8 something. And then also, the gradient of f, the last thing I said, I think at the end of class last time, was that this vector is perpendicular to the level curve of f through P. And I'll show you pictures of this in a second, but the thing is, like, yeah, like there was the whole ramp thing. I just keep this ramp picture in your head all the time. You zoom in on the surface. Again, the direction and magnitude sort of tell you the way that the tilt, the way the tangent plane's oriented and its amount of tilt. Because the more it's tilted, the steeper the rate of increase if you go in that direction, right? I should say this is a compass direction, like a 2D direction, not a 3D vector. Maybe compass direction. It's like if you're standing on a ramp and for some reason you can't see which way to go, but you have some magic compass that tells you which way to go up the fastest. Then you'll like look at your compass and it says, oh, go that way to go up the fastest. So it's just like a direction, like southwest, northeast, you know? If that makes sense. Because that's a 2D vector. I guess what I'm trying to, the thing I see students, I think I'm preemptively trying to do, interrupt something that I see students do a lot, which is the gradient is actually this vector pointing almost like into the ramp, not this vector pointing up the ramp, because that would be a 3D vector. And this is a 2D vector because it's just, there's no Z component. Okay. Things to keep in mind. Here I drew, so you can actually plot. So the gradient's what's called a vector field. Let me share. The gradient is what is called a vector field. And you can see because at every point there's a vector, right? And so you get this nice field of vectors. And we're going to be looking at vector fields a lot later in the course. So it's worth mentioning now that this is our first example of this. And yeah, and And if you actually overlay this with the contour map of this function, so here's the vector field. Notice it's 2x plus y comma x. And there's a command called vector plot, lets you do this. By the way, all these vectors are the same length, so the colors are for longer vectors. Like I think the brighter colors represent longer vectors, because if you try to draw the length of the vectors on the picture, they'd start to overlap each other. It would look horrible. So they sort of normalize them all to be like unit vectors. And then they just shade them with colors based on how long they are, like what the actual magnitude is. Here's a contour map, and if I overlay them, then I think you can start to believe that the gradient is perpendicular to level curves. Starting to feel, right? Yeah. Yeah, everywhere it's sort of perpendicular. You could probably play with the number of contours and make it like so that each of these is perfectly on. The tail of each vector is perfectly on a contour or something, but you get the idea, right? So yeah, so this is a nice picture to keep in mind. And notice this is kind of the opposite of the picture of the particles going down the surface. Very hard to like rotate, but this is kind of a top view. And notice these vectors are going down, like to the left a little bit down, and these particles are going to the right a little bit up on the picture, right? So this is a nice way to visualize these things sometimes. We could give the field itself in this, oh, hello. These are kind of fun. What did I say, 2x plus y, comma x. Parse error in expression. Maybe I need 2 times. Oh, yeah, there we go. Oh, interesting. This actually is not going down. This is going the correct direction. Oh, hello. They've updated this app since the last time I used it. This didn't used to be there. That's kind of cool. You can move around and see. I think this was written in like Java like a million years ago, and then somebody's finally updated it to like since Java, like Java applets were a thing like a million years ago. And now they don't load very well. So yeah, but you can do the field arrows. Yeah, so this is just the arrows. Oh, we're going to talk about curl detectors at some point. That's also that's like teasing late November, early December. But yeah, but it's sort of fun to play with these. Just fallstad.com/vector. If you get bored in class, I want to play with it. Don't want to listen to me talk. I don't know if it works on the iPad, actually. Probably. I think, again, it's something that they made. Anyways, okay. So does it all make sense for 2D? At least what the 2D gradient is telling you. I'll give you examples to work with. But let's go back. So, okay, now, the next thing is I want to motivate the 3D gradient, but I want to sort of see, I want to motivate it with the 2D gradient first, rather than go up the dimension and get to things that we can't. Like if I go up to 3Ds, now we're looking at a graph. The graph would be 4-dimensional, and then it's harder to picture things. But let me do something that seems kind of random at first, but it's going to connect back to this. So, so if we go back to just functions of one variable, or if we're really staying just in the plane, we're not really going into 3 dimensions, like not z equals f of x comma y, but so let me say, so here's a useful application of the gradient. A useful application, I mean within mathematics, not like in the real world. It sounds like I'm saying something. Do you remember ever in calculus, single variable calculus, being given, I thought somebody just said no as soon as I said that. Do you remember single variable calculus? Somebody's like, no. Do you remember given sometimes something that was not a function where you couldn't separate the x and get y as a function of x, and then you're asked to still like find the derivative? So here's a reminder or an example. Say an example. Say we had the function xy squared plus x cubed y, or it's not a function anymore, it's just an equation. It's an equation. Equals like 6. So I think the point 1, 2 satisfies this equation, I think. What is, you could ask a couple of questions. You could ask what's the derivative at this point? What's this equation of the tangent line? Like this is some curve, right? This makes a curve in the xy plane. What is the equation of the tangent line? Into this curve at this point. Or what's the derivative? What's the like rate of, what's the slope? We could plot this actually. Actually, we can plot equations using contour plot and the double equal sign. So I know you can pause the share, but I think when I did that one time, the video never went back to the Blackboard. It just stayed on the screen. So I'm actually stopping and restarting the share each time. So x times y squared plus x cubed times y equals 6. Does anybody have any idea what this looks like? I don't. And I'm a professional, supposedly. I don't know what this is going to look like. Okay, I don't know if that's what I. Oh, hello. Is that what you guessed? Exactly what you guessed. Let's make it a little bigger even, because that's an interesting little third hump. Okay, interesting. So the point 1, 2 is over here somewhere. And so there is a tangent line and there is a slope, right? There is like a derivative at that point. Do you remember how you had to go about finding such a derivative? Say it loud. Implicit differentiation. Remember implicit differentiation? Was that your favorite topic? Yeah. That's the thing where you could differentiate both sides of this with respect to x, and then use the chain rule and the product rule and stuff. And so you would end up getting like dy dx's, and then you could solve for dy dx and get that as a function, in terms of x and y. So I claim that now, if you think about this in terms of multivariable calculus, there's a much easier way to do it. You don't have to do implicit differentiation. So the sort of AP Calc way is what's called implicit differentiation. I've always found it's one of the least favorite topics of students when I teach calculus. The multi-way, well, let's reinterpret this as a level curve of a function of two variables. Think of this equation as the level curve of f of x comma y equals xy squared plus x cubed y at level 6. Right? We're just setting that equal to 6. okay. Well, we can do the gradient. We can take the gradient of this. So what's, I stopped, oh, I didn't stop the share. I knew I didn't stop the share. They're supposed to yell at me, start yelling at me. Okay, so, oh, I have to hide myself. I don't like when I show up on screen, okay. So, all right, take a minute and compute the gradient of this, and then also then do the gradient of this point. Yes, take a minute and do that. Grad f of this function is equals something. It's probably bigger, maybe not. And then grad f at the point 1, 2. Good practice with partial differentiation. Enough room here. Look around and look awkwardly at people's papers.
Take it for your credit.
Good. The numbers get pretty big or no? Hi. What's that?
We're deciding. I thought we both got different answers.
Oh, that happens a lot.
Yeah.
Seems like half of my office hours are students coming off. They got different answers for a problem and they're trying to figure out who's right or if neither of them are right. Okay, so what's the partial x here? Someone tell me. Y squared plus 3x squared y. Yeah, you're treating the y as a constant here, right? So that's good. And then what? Two xy plus x cubed. And then when you plug in the point, 10, 4 plus 6 is 10. And 2 times 2, 1, 4 plus 1 is 5. Good. 10, 5. Interesting. Is that plausible on the picture of the graph at this point? 10, 5 kind of points that way, right? So it's plausible. That's exciting. Can someone tell me the slope of the tangent line at this point? Just knowing that that's 10, 5. The gradient is 10, 5. You're going down, okay. Do you have a number? Negative 2? Slope negative 2? Why do you say negative 2?
When you dot that A, B solve for 0.
Yeah, if you want a vector perpendicular to this, you just swap the numbers and make one negative. And that would follow, that would kind of be tangent to the graph. And you can sort of see that it would be like, you could do like 1, negative 2. So that'd be the vector over 1 down 2, which is slope negative 2. So that's fast, that's the fast way to do it. But the more direct way to do it, I mean, the sort of is what once we had a gradient vector We have a vector normal to the curve. So it's also normal to the tangent line, right? Draw this. Maybe I'll try to draw this and then try to draw this vector. So yeah. So, right, so we have this, we're at this point, the point 1, 2. We see that the curve goes through it something like that. We have this gradient vector, it's kind of long. Of course, it's a multiple of 2, 1, so like you could just, if you just care about the direction. I mean, this is important if you want to think about this as a function of 2 variables and think about the rate of increase. But if you just want to think about perpendicular, you could just say 2, 1 there. And then we have the tangent line at this point. So this is tangent line. This was the point 1, 2. This was the gradient of our function at 1, 2. And this was the curve. This was the curve given by xy squared plus x cubed y equals 6. Okay. And so notice that the gradient is perpendicular to the curve at this point, like because it's a level curve. It is a level curve of a function of 2 variables, so it's perpendicular to that. It's also perpendicular to tangent lines. So in fact, for this line, we have a point and a normal vector, and we figured out how to write down the equation of a line given a point and a normal vector. So given point 1, 2, normal vector 10, 5, the equation of the tangent line remember this, it was like 10 times x minus 1 plus 5 times x minus 2 equals 0. Nope, not x, y. Right, remember that? Sort of the coefficients of x and y, just like in 3D, it's the coefficients of x, y, and z. Give us the plane equation. And so, right, you could divide through by 5 at this point if you wanted. And then you could actually solve for y in terms of x if you want. So I think y equals negative 2x plus 4. And there's your slope of your tangent line, negative 2. I mean, there's your like derivative at that point. So you could still do the implicit differentiation way, but this math here is a lot more simple, which is nice, right? And if I wanted, I could add in that equation to the picture. Something like this. So if I put both, just as check. There you go. That's satisfying, right? Okay. So that's nice. It's like, so right. So now given any curve, like not just like y as a function of x, but given any curve in the plane, this is actually in some ways a faster way to find the tangent line at that point. Is just to take the gradient and use that as the coefficients of x and y in the tangent line. Cool. Cool. All right. So now I want to go up to 3D and think about functions of 3 variables. Because this is gonna, the same idea is gonna work there. So yeah. All right, so let me go back to the board here. Okay, so Yeah, let me introduce. Let me do this. So, of 3 variables. Okay, 3D gradient. So now we're given, W is f of x comma y comma z. I'll give you sort of a simple example. Start with a simple example. Let's do the function x squared plus y squared plus z squared. It's a function of 3 variables. One thing you could say that it measures is the square of the distance from the origin of that point, right? The point x comma y comma z, if you plug it in, the distance from the origin is the square root of x squared plus y squared plus z squared. So sometimes it's good to try to think what these functions could be measuring. Like when you think of functions of 3 variables, like because we can't imagine the 4th dimension, a lot of times you want to use like some more conceptual notion of what the output is. Like you can imagine a temperature map of this room that measured the temperature at every point in this room. So that would be like a 3 variable input and a one variable output, something like that. Here, so yeah, so this actually measures square of the distance from the origin. The gradient of f in this case is just, now it's going to be partial x, partial y, partial z. It's a 3D variable, 3D vector, which here is not too bad, right? It's just 2x comma 2y comma 2z. And the thing I guess I want to claim is that all the same interpretations that we had for the 2D gradient work for the 3D gradient. So 3D gradient has the same geometric interpretations, just up a dimension. As the 2D. So the direction is the direction of max increase of the function. If you have a function that measures, like that's the origin down in the corner there. Each point in space, you're just measuring the square of the distance from the origin. Which direction do I head to increase that function the most quickly? Directly away from the origin, right? Like if the origin's there and I'm here, I want to go that way to increase. Right, if I go over there somewhere, then it may not be increasing at all. So the fastest way to increase your distance is just to go straight away from the origin. This vector actually points straight away from the origin. I mean, it's worth mentioning that like, it's kind of weird to think about, but if we're at the point, maybe I should even give like a 2D version of this. Let's just do 2D version of this real fast. Like the vector 2x comma 2y, if we're at the point x comma y, and we want to think, just like with the gradient pictures I showed you, we want to think of the vector coming out of that point. Then the vector 2x comma 2y is like that, right? So it's points directly away from the origin. I'm just doing this because I can't draw it in 3 dimensions as compellingly. Right, and this actually has a special name. Sometimes the vector x comma y in 2D or x comma y comma z in 3D is often notated as the vector just r. So r is x comma y, r is. It's like a radial vector kind of. So that's we're gonna see this more and more. We're gonna use this. So I could, if I wanted to, I could write, I'm not gonna do that. I'm not gonna really do it here, but it'll come up later, but we could write this as 2r if we wanted to. And r is just a vector pointing directly away from the origin. So if you wanted a vector pointing directly towards the origin, you'd use like negative r. Actually, there's a way to write Newton's law of gravitation in terms of like vectors, and you have to use a negative r vector to point towards the center of your object if you want to state, you know, because Newton's law is about the force, right? The gravitational force. And forces really should be a vector, so it really should have both a direction and a magnitude. So I'll revisit this, it'll come up later. I just kind of want to say it now while we're writing this down. But in this example, right, so we had 2x comma 2y comma 2z. So that still has, right, it still has the same geometric interpretations. Maybe I should write down with, you know, again, the magnitude is the direction of max increase. The direction is the direction of max. Wait, sorry, the magnitude is the size of the max rate of increase. The direction is the direction of the max rate of increase. Yeah, I'm on. Well, the gradient is a vector, right? It's one vector. So at a point, it would be one specific vector again. But you actually anticipated what I want to say next, which is that now it's perpendicular to level surfaces instead of level curves. Yeah, it's orthogonal to level surfaces. So in fact, yeah, so the same geometric interpretations as 2D. I guess I wrote that up there and then put a colon and then did something else. So the 3D the geometric interpretations are, I guess the magnitude and direction are exactly the same conceptually. As 2D gradients, it's just the max rate of increase and the direction of, yeah, max rate of increase of f and the direction of max increase. And exactly what Milana was just getting at, it's also grad f at a point is perpendicular to the level surface or the tangent plane too, if you want to think, because it's that thing sometimes when you say perpendicular to a curve, you really mean perpendicular to the tangent line because you zoom in on the curve. And the same thing here, yeah. Orthogonal, perpendicular, and normal, I'm kind of just using all interchangeably. So I could say orthogonal, I could say normal.
Okay.
For some reason, actually, probably the word we use mostly in terms of, especially if we want to think about surfaces and tangent planes, is normal, perpendicular / normal to the level surface. Now it's a level surface instead of a level curve of f through the point P. So that's the only difference between the 2D, is just instead of being perpendicular to level curve, it's perpendicular to level surface, right? So, I mean, I think in this simple example, it's kind of clear that like the direction of max increase is that way. We could actually write down, if you want to think about it for a sphere, right? Like, let's say, Yeah. As an example, what's the tangent plane to x squared plus y squared plus z squared equals 14 at the point 1, -2, 3. I think if you plug those in, you get 14. So what's the equation of the tangent plane? So if you think about it, so that's actually, it's funny because the gradient has this interpretation, but the way we're actually going to use it is very similar to what I was just showing you with finding the tangent line to curves, where the curves are not just functions y as a function of x, but actually equations involving x and y inextricably tied up in ways that you can't isolate one or the other. The same thing here. It's like, it's actually a very useful thing because we're going to look at lots of surfaces that aren't nicely just z as a function of x and y. And we're going to want to be able to write down like the tangent plane. And so it'll be the same idea. Like you could do this, like think about before today, like what we've done was like, we used the partial x and the partial y of a function of 2 variables to get the tangent plane, right? So you'd have to solve this for z, you'd have a square root involved. You know, z is the square root of 14 minus x squared minus y squared. You'd have to check if you're the plus or minus. I guess z is positive here, so you'd be on the plus, right? This sphere, you can think of it as 2 surfaces, like the top hemisphere and the bottom hemisphere, if you want to give them as functions. But this itself is not z as a function of x and y. So you could solve for z, find the partials, plug in, get the tangent plane, but it would not be that pleasant, right? Here, it's much more pleasant to just take the gradient at this point. That gives you the normal vector, and you're done. Because as soon as you have the normal vector in a point, you can write down the equation of the plane, right? So we just said the gradient of f, well, so again, think of this sphere as level surface of the function f of x, y, z is x squared plus y squared plus z squared at level 14, I guess. I just picked 14 to make this point satisfied. Right? Then the gradient of f is actually perpendicular, which is 2x, 2y, 2z, is perpendicular to this surface, to the sphere, at any point on the sphere. So in particular, at the point 1, -2, 3, it's right. So at 1, -2, 3, the gradient of f is, what is it, 2, -4, 6, which is, and I want to say that this is really n, normal vector at this point. Normal vector to both the sphere and the tangent plane. Right? The sphere is like this, the tangent plane is like sort of similar. I mean, when you zoom in on the sphere, it looks more and more like its tangent plane, right? And so then the equation, remember what we do is we just use these as the coefficients. I keep using x's. So that's the equation of the tangent plane at that point. And I could divide through by 2. In fact, that's funny, the 2 is not really necessary if we're just caring about direction and stuff here. Does that make some sense? Yeah. Yeah.
Why is it not plus or you have to switch the sign to my value?
I think just because I have a -2 right there.
Okay.
Just, yeah, I just I wanted to throw in a minus sign. The 0.1, 2, 3 also satisfies this equation. I just was like, I'll throw in a minus sign somewhere just to make it interesting. So yeah. So you can actually write down like, and then anything else that's complicated, like we could write, as long as any equation basically at x, y, and z now, we could subtract everything to one side, all variables over to one side, and then make that a function of 3 variables. Take the gradient, get the normal vector, and then write down the tangent plane. Same idea. So this is actually, so it's funny because I taught you that tangent plane equation, or you learned the tangent plane equation. The z minus z naught equals partial x times x minus x naught plus partial y times y minus y naught. I actually think of that as being like not what I use most of the time. I would use this. And in fact, as a last thing, I can show you how they match up. It's sort of interesting. There's an interesting thing here. Yeah, like what's the, can we directly connect this to our other tangent plane equation? So in some sense, like, I guess what I would say is in general, actually, I'm going to use the letter G instead of F. For G of x comma y comma z equals constant at the point x naught comma y naught comma z naught, the tangent plane, if I just kind of if I'm just kind of writing in general what I did here, the tangent plane is the partial x times x minus x naught plus the partial y. And I really mean plug in the point. I just don't want to write g sub x of x naught comma y naught comma z naught. Just gets kind of busy. Plus partial z equals 0. So that's the tangent plane equation. Okay. That's all we did up there. We just plugged in the partials and then multiplied times. Because this vector, these are the coefficients of x, y, and z, and we know those make the normal vector of the plane. The gradient also is normal. So that's why we're going back and forth. Now my question is, how does this connect to this version, z minus z naught equals f sub x times x minus x naught plus f sub y times y minus y naught in the z equals f of x comma y case. That's why I renamed this G, just to like think about the difference between these two situations, right? Either G is, either it's a level surface of a function of 3 variables, or Z as a function of 2 variables. So how does this connect? I think I should put a question mark there, right? It's a question. Well, we could rewrite any surface as a function of 3 variables. I mean, I could write this, I could subtract the Z over to the other side. So let's do that. And maybe I'll write an example next to it just to. We could rewrite this way. So for example, if we just had Z equals X times Y or something like that, right? I'll use our X squared plus XY example that I kept using. So we could write X squared plus XY minus Z equals 0, right? And what's the, now I want to think of this as G of 3 variables, function of 3 variables. So what is G sub X? What would G sub X be here? 2x plus y? Remember, that was f sub x when we consider this as a function of 2 variables. So notice G sub x equals f sub x. G sub y is f sub y. Partial y's are the same. Right? Partial y here is just x. But what about the partial z? What's the partial z here? -1. And I guess what I'm saying is, which I'm cognizant I'm going to run out of time, is that if you compare these two to each other, and I put f sub x here, f sub y here, and -1 here, this converts exactly into that if I just add this term over to the other side of the equation. Right? So plug those in up here, and you get the same equation. So it's kind of interesting because we took a long time, we took a different route to derive this equation. We took this whole route of like looking at the picture of the plane and the partial x and the partial y and seeing how like this is the equation of the tangent plane. This is a different approach and we got the exact same answer, sort of much quicker. So it's nice. You can go back and forth between the two. All right. Oh, we're out of time. Sorry. Thank you, everyone. Thank you for helping me with the Zoom.